So we built this mobile robot already. It's in our lab. So I think later on, if you choose to have some design of this robot, we can share some of the CAD design of the bottom vehicle to you, and also we can bring you to the lab to take a look at the real robot. So why do we build this huge robot? Because we want to have this huge industry robot that has a 70 kilogram payload, which means it can carry something in a weight of 70 kilogram, a person's weight. So it's a super huge robot. If you think about try to imagine how big it is, you can take a look at, you think about how much moment this 70 kilogram could generate when a robot is doing some motion like this, configuration like this. Basically lengthening its arm, grabbing 70 kilogram, multiplying the length of its arm, it's gonna generate a huge amount of moment and apply it to the shoulder. So this is why most of the industry robot you have seen probably can only carry 5 kilograms or 10 kilograms, because the moment applied to the shoulder motor is very large. And if the item is too large, it doesn't lift. The motor at the shoulder cannot generate enough power to lift the item. But this one has no issue, so it can carry even a person. And since we want to carry a large workpiece, we purchased this huge KUKA robot arm, and we want this robot arm to be able to move inside the factory. That's why we need to build this vehicle at the bottom. And when the student made the design, I think my student made it really, really strong, super strong. So it's actually too strong. So I can show you more details about the robot, also the bottom part. So this kind of wheel is called a mechanism wheel. It has a name, mechanism wheel. It has some rollers at the surrounding the wheel, and it has this diagonal arrangement. So when you spin the entire wheel, you actually have those rollers contacting the floor, which generate not only the reaction force along the vertical direction, it also generates some reaction force horizontally. So for every mechanism wheel, there's always forces in all directions, both the radial direction and the axial direction. By controlling all 4 wheels individually, you can rotate this one clockwise and then rotate this one counterclockwise. They are individually controlled. By control them individually, you can have this kind of vehicle move forward, backward, left and right, even do some spinning, clockwise or counterclockwise. And the wheel itself is actually 70 kilograms. It doesn't look like it's a 70 kilogram wheel. It's not super large, it's like this, like a wheel of a car, maybe a little smaller, but it has many metal parts inside, so it's very heavy. Okay, usually we have 2 students to carry 1 wheel. And since the wheel itself is super heavy, you need a large motor to drive it. So the yellow part right here is a motor and also decelerator. In between, there is a shaft system. So the design of the shaft is very, very related to this course. The two green parts actually are two bearings. The red one is so-called the coupler. Basically, it allows you to connect the shaft inside the motor and the shaft right here. So two shafts were being connected by this rubber coupler. So this is the original design made by my graduate student maybe 3 years ago. So overall, you can see, if you see from the side, there's some bolts right here that connects the bearing and the bottom plate. So only several bolts right here. So if you take a look at the entire plate, here is a super heavy weight coming down, right? And there is a bearing. And there is a wheel. And there is a motor. And here are some bolts connected. I think that's it. These are the only thing that is connecting the shaft system and the bottom plate. So you can almost say the bolts right here has to carry almost 90% of the entire weight, right? And also, because of the heavy weight right here, maybe the bottom plate could be bending in this shape, right? And also, for the shaft itself, you have the wheel, and here are some reaction forces, right? And you have super strong force pulling on the right hand side. You can say it's around one quarter of the entire weight. You can say that. And you have basically, so this is like where you have the bearing, right? So the shaft itself, and of course here's where you have the motor. The shaft itself is carrying super strong shearing force right here. And if you use what we have learned recently, will there be failures, or will there be fatigue issues, right? So is the diameter of the shaft large enough? If you want the shaft to be stronger, then you may need to design the shaft in this way. Because the diameter right here inside the wheel cannot change. You have to have some certain dimension to fit into the hole inside the wheel. So if you want the entire shaft to be stronger, probably you can only enlarge the other parts, some other parts. But when you do that, you may have stress concentration, right? So there are issues about the shaft design, and you need the knowledge about bearing itself, bolts. So there are many mechanical parts in this design only, and for the following weeks we will be talking about some of the parts, but that doesn't cover every required knowledge for the design. If you are focusing on, for example, the chef design for this robot or the plate or something else, you may need to work with your teammate and study further, study into the part that you are more interested in, and make proper design. Okay? So, the vehicle itself, there are many things to work on. The initial design has the vehicle without the robot. So the total weight of the vehicle is around 700 kilograms. So the vehicle is I remember 740 kilograms. And I remember the wheel itself is around 70 kilograms. So you have 4 of them. That means if you do not care about the self-weight of the wheel, because the floor is carrying the weight of the wheel, then the body has around 300 to 400 kilograms. Right? So this middle part is 300 kilograms. Maybe you can reduce the weight by cutting off some of the materials. If you do that, then the forces applied to the ship will be reduced. And of course, when you do that, your structure will be weakened and you will see some deformation. Maybe you cannot reduce the structure too much. So that's what's interesting about the design. Sometimes you want your design to be stronger, sometimes you want it to be weaker, and you can work with your teammates and figure out what will be the best. So this is the mechatronics for the system, which is not related to this course, so you don't need to worry about this. Just to show you the dimension of the entire vehicle. It's funny that we have a wider width than longer than the length right here. So I sometimes feel like our vehicle looks like a crab. It's not longer. It's not like our daily life car. Usually it's longer this side, the thinner on the left from the left. But for our design, we are wider and shorter for the front and back direction. So yeah, you can say it looks like a crab. And this is the height of the entire thing. So it's actually a pretty tall robot. I'm 180 centimeter high, so this is like 170. So it's like this tall when it's having this posture. Okay, and this is like a control part. You don't need to know about these. Those are not important. Okay, a video. Because the entire robot is too heavy, so the floor was damaged. So far, no one is hurt. Nothing was damaged. So far, it's safe. But it's not an easy research. Okay? So you can see that when the vehicle is moving sideways, it relies on different directions of rotation for both wheels. So it allows you to move sideways. And over here you can see the wheels can be moved while you are having motion in the hand. So it's like they can be controlled at the same time. Later on, this is more advanced. I'm not sure if I'm not sure if any team can reach this part. But if you want, I'll let you know what will be the research that can be done, which is a little bit related to the project. So the positioning of the vehicle is not very accurate, which means we rely on sensors to detect where the vehicle is. However, the sensors are not accurate enough. We are using laser to measure the distance from the vehicle itself and to the object. And it's called a LiDAR. LiDAR. Okay, so it's basically beams of laser, and the laser is being rotated by 360 degrees. So you will have beams of lasers measuring the distance from the sensor itself to whatever the laser hits. So it's a system that allows you to have distance measurement in all directions, 360. Okay? By doing so usually you will see something like this when you heard about indoor navigation. This is a vehicle and you have lasers hitting the wall like these. And it's telling you what's the distance for each measurement. So it's like every time a laser hits somewhere on the wall, it gets one sampling point. So mapping of the vehicle inside the space usually relies on those sampling points on the wall. And if the measurement right here, for example, L, has an error, if there's an error, then you will accumulate a lot of errors on those distance measurements. Which means the system relies on those measurements to find where it is, just like your vacuum machine on the floor. It relies on similar technology. But for vacuum machine, you don't care about how accurate it is, because it's just a vacuum machine. If it's inaccurate in a scale of 10 centimeters, so what? The vacuum machine will do some routing to explore the space. So even though the vacuum machine has a inaccuracy of 10 centimeters, that's okay. But for robot, it's not good. Because for robots, we want to move to somewhere and pick up something. If we have poor accuracy on our own positioning, we thought we can get the cup of coffee, but we missed it because we thought we were here, but in fact we are here. So when we reach, we missed the target. So positioning is a very important topic for mobile robots. And also the dynamics of the vehicle is also important. Because if we build a structure that is not very stable, when you move your item, which is heavy, you could be vibrating when you move. So you could be unstable when you move, right? We don't want that as well. So in this research, we use a camera at the tip of the robot arm. So right here, right here, there's a camera. Let me use the laser pointer. There. I don't know why my computer is slow. Okay, so there's a camera at the tip of the arm, and we try to take pictures of those binary codes, so-called the ARUCO code. So there are algorithms to figure out the distance between the camera and the ARUCO code, which is more accurate than LiDAR. Better accuracy, slightly better. So we took a picture of, you can see in my lab there are multiple ARUCO codes. The camera will figure out, okay, there are 5 ARUCO codes there. Take 5 measurements from the camera to the ARUCO code. Use some algorithm to figure out where the robot is. And that will reduce the error a little bit more. By doing so, like this, okay, the camera at the robot arm take some pictures and then measure its distance to the ARUCO code. It requires multiple ARUCO codes. Doing some algorithm, it was able to figure out the position of the hand. What do you do next? You will study the dynamics. So it's like you are moving your robot arm in the space in a certain way, and then you figure out how stable your robot arm is. So we ask the robot arm to move. This is only moving along some y direction, moving forward and then moving backwards. So linear motion, right? So by doing so, in fact, for your motor, the motor doesn't know the robot itself is not stable. So for the motor itself, if you have an encoder inside the motor, and you assign some command to the driver which drives the motor basically doing some motion, allowing the robot to move linearly along y direction, back and forth. The motor and the encoder doesn't know it has some positioning error. So we use we actually use another set of laser to figure out the real accuracy. So in fact, the real trajectory of the robot arm will be the red color. So it's not exactly the same as the position of the encoder. So why is this related to our research? If you weaken the structure, the total weight of the vehicle reduces, which is good because you provide lower payload to the mechanical components. However, when a structure has lower mass, then it's more unstable. It could vibrate. So when you have weaker structure, the positioning error could be larger. Okay? So we did similar motions along x and y and z direction. You can see that when a robot is doing something like this, going back and forth. So when it's changing its direction at the final position, like a tip position right here, you sometimes will overshoot. Okay. So we use the Aruco code to take the same measurement. We did some experiments. So you remember the student did some comparison. Yeah, so this is a comparison between laser and also the Aruco code. It's the trend is similar. Okay, but anyway, if you are let me see, is there some results? Okay, so the Aruco code measurement has an error of 6 or 7 millimeter, which means if the robot arm is having a 100 millimeter distance away from the cup, and if you use the Aruco code method to determine the distance, it's around 100 plus or minus 6 millimeter or 7 millimeter. So again, it's not very accurate. But if you use LiDAR, it could be 10 millimeter or 20 millimeter or even more. Okay, so in this research, positioning is a challenge, and also if you are on the motion, if your robot is trying to grasp something while moving, then the unstable motion is another level of difficulty. Okay, so these are the topics that is related to this vehicle. Now I want to show you the second vehicle. So the second vehicle looks like this. It's actually a vehicle from an industry project. Do you know, do we have the vehicle already? I think they shipped back. Yeah. So we work with ITRI, 工研院, in the past on an industry project. And this is a robot that really can perform inside a factory. Now the project is finished, so the vehicle now is back to our lab. And this design is a very special design because how the product looks like. I will show you what's the product about. Let's see. Yeah. So, in many electronic devices, now we have soft circuits. So it's like a membrane with soft membrane with circuits. So those are very important technology in the industry. Let me tell you what those are. Something like this. Soft electronics. Okay, so how do they make those? They have a row of those. Like this, like a row of films or membranes. And they use semiconductor technology to pattern the circuit on soft membranes. And inside the factory, when they built something like this, maybe I have a video to show you. Yeah. So basically, we have rows of those soft circuits, and they are being rolled inside a cylinder, a tube. And for the company, they want to use a machine to inspect all the circuits on the roll. So one way to inspect every circuit is to unroll the entire roll. So they put this roll of circuit in a inspection machine. The machine will unroll it. So basically open it, and they have camera to take a picture of everywhere. Once the circuits are being inspected, they rolled it back. Okay, so the manufacturer produce soft circuits and then wrap them into the roll, deliver to this company. This company have human worker carry those rolls, put it in inspection machine, run the machine, just like rolling the tape. They will unwrap the roll, use camera to inspect, and then roll it back. Once they found, okay, there is a damaged circuit, they need to take it off, because you don't want your cell phone or your mechanical electronic device has defect, right? So let's talk about the vehicle itself. Why do we bring the robot for this mission? Because this roll could be quite heavy. The roll could be as heavy as 30 kilograms. And in the factory, most of the workers are female workers, because they think young female workers has better eyes than male workers. And for this kind of task, they sometimes need to use human eyes to have some observation. So in the industry, in the production line, sometimes they hire young female workers, usually in the age between 25 and 30. That's what the industrial people told us. Young female workers has better eyes, better patience, handling, good hands of handling. So since they hire female workers in the factory, they face an issue. Those parts are too heavy for them. So they want us to deliver this robot, basically grab the roll, take it out from the shelf, and then deliver to the inspection machine and put it in the inspection machine. That's what the system was about. So it looks like this. There's a upper half and the lower half. The lower half is basically a vehicle on the left-hand side right here. The upper half, there are several motors which allows this platform to change its height, because sometimes the part is located at different levels. And also for the machine, sometimes you put the roll right here, sometimes you put the roll right here, different heights. So this platform allows you to move up and down. And there's a motor right here, allows you to move forward and backward. That's only 2 degrees of freedom for the upper part. Because the vehicle itself can do alignment. It's also based on mechanism wheel, so it's able to move left and right, forward, backward, change angle. When it aims properly, the robot move up and down, forward, backward to take the part, and then move to the inspection machine, put it in. Okay, something like that. So when they do this, they made the system super strong. Way too strong. Okay? So I think there's a lot that you can work on in this particular design. There are some videos about how the vehicle move forward, backward, left and right, do some self-spinning. Okay. Let's talk about the system on the top. So basically, you can see my student made some mechanical design. She tried to analyze what's the required torque and choose the proper motor. And over here, did she analyze whether there is stress concentration? I don't think so. She did this. She analyzed the deformation inside the base plate right here, the purple one. And you can see she studied the safety factor. So what is this model? So this is basically comparison with yielding. It's not even the right model. Okay, so if you study the maximum shear, then you can have maximum shear stress model, right? Divided by 2 and safety factor, right? If you do this, that's maximum shear stress model. This may not be right because this is I'm not sure if it's von Mises stress, maybe. Oh, if it's von Mises stress, then it's right. If my student was a female, so if she did von Mises stress, then she's using von Mises stress smaller than yielding strength and then safety factor. This would be the maximum distortion energy model. Right? So if she was doing that, then this is the right equation. But if she is only studying principal stresses, that may not be right. So in your project, you need to know what you're working on. Okay? I would say the maximum distortion energy with von Mises stress will be the easiest way to do it. Okay, because the software helps you to compute von Mises stress. You can directly apply this simple equation. Okay. Maybe we take a look at the entire video. So you can see there's a gripper, but the gripper doesn't actually grasp. The gripper has 3 fingers and it doesn't grab the cylinder from outside. It actually expands to tight to how do you say that? To grasp from the inside. So it's a way to hold the cylinder. The cylinder is outside. The reason why is because the circuit that is wrapped outside of the cylinder, and they are very expensive. They are the customer's product. You don't want to damage the circuits. So the only good way to grab the entire roll is to grab from the inside. Okay, so that would be the second robot that you can work on. So either either way, and I want to introduce you what I am interested in for the third topic. I remember I mentioned last time, it's about the QUBIS satellite. Okay, so Cube satellite sometimes has a design of using the origami solar panel, something like this. Let me see from which lab. Tokyo Tech. And many other, or maybe do I know any of the professor here? Let me see. I'm not sure. Anyway, so this is research done by Tokyo Tech and many other universities and companies. So you know, we have collaborations with Tokyo Tech. They have been studying how to have basically foldable solar panels in Cube satellite. And of course, for us, we won't build something like this. We just want to study. Okay? So take a deeper look. So basically, Cube satellite looks like this. Then this is a 3-unit Cube satellite. So basically, for Cube satellites, they design in units. So every unit is like a cube. Okay, so this is a 3-unit satellite. And you can see on the right-hand side, they use some space at the surface to have this origami. Origami is like a folding paper. Origami design for the solar panel. So I'm very, very interested in how this can be done. I think this is showing the sequence, the mission sequence. Okay? And this is very interesting. See how they have membranes for the solar panel. Okay? And this is the idea, how they unfold the piece of the membrane. Okay? So originally in this shape, gradually expand so they can open this membrane. So this is a deeper look. So very interesting. Okay? Another reason why we want to do this, because recently our government would like to investigate in space engineering. Taiwan Tech is not the main university which work on space engineering. I know Cheng Kung University is. Central University also is another school, and also Yang Jiao Tong. They are the main universities which have space engineering projects. However, some professors in Taiwan Tech in the past few years started to think about how we can contribute in this kind of topic. So I kind of want you guys to look into some of the research papers of CubeSatellite. If you are interested, you can make your own design, CAD designs. And I want to, when you design this, I want you to take a look at what would be the mechanical design for some of the parts in there. It doesn't have to be exactly same design, it can be something else. So you can look into many different research papers and choose one of them or modify one of it. Once you do that, you can use software to study the strength. Is the design strong enough to carry everything that is required? Is it strong enough to be able to expand without breaking? Yeah, something like that. So I think this time I have 3 different topics. One is the mobile robot with a robot arm. The other one is a mobile robot for role inspection. The third one is a CubeSatellite. So after today, please start to look into your friends, see if you can form a group. I don't want to randomize you guys this time, just find your own friend. I know some of you may not know other classmates. So for whoever knows each other that can form a group, let the TA know who's your teammate. And whoever that doesn't know anyone, you can wait, and then the several couple people that doesn't have a group, I will just randomize your grouping. Okay, so I will let you group by yourself, and when you group, please let me know who is the team leader, and let the TA know who's the team leader, and pick up one topic. So the 3 topics: AMR with the robot arm. Second one, also an AMR, but for the inspection. The third one is the so-called CubeSat. CubeSat. Mechanical design inside a CubeSat. Okay? So that's it for today. I will ask the TA to send you the files that I present today, so you can have several days to look into the 3 ideas. And before next week, you will let us know which topic you want to work on. I hope we have some groups for every topic, so we don't work on the same topic. And of course, you can choose your own topic. You can just say, I'm not interested in those, I want to do this. But make sure when you propose the idea, you are going to focus on mechanical design. So there should be some shaft, gears, pulley, bolts, so that you can work on some mathematics for the design, for the selection, for the components. Okay, so you can even focus on a bicycle if you're interested. So if you are working on a bicycle, you want to make a drawing of a bicycle. But usually when students pick up their own design, their CAD drawings are not realistic enough. They are usually very simple structure like cylinders, boxes, not very realistic. So I will recommend you to choose one out of the 3 because they are already realistic designs. And your task is to study into the real design we will give you the CAD drawings, and you can start to make modifications in the CAD software. And letting us know, if you do that, what will happen in the strength of the parts, and also like the stability, you can study further, right? But if you design on your own, then you are responsible for making a proper design. Okay, I don't know why whenever I allow students to bring up ideas, they like to bring up bicycles, guitars, paintball guns, and I don't know the name of this, like the rock throwing machine. So I think students like something like those, I know. But usually they make drawings that are still not very realistic. Okay, so please make up your mind, and I hope every group has their own idea. Okay, so I will let you guys figure out who are the team members. Maybe you can use right now to figure out. Students in this year. Only 12, right? Only how many? So only one person is not here. If you are here, you can already form groups. I would say 3 or 4 people in the group. So if we have 12, that would maybe 4 groups, I would say. So maybe 4 groups, one group choose one topic. Okay, so you guys figure out. If you can make a decision, you can tell the TA right away. That's it for today. Any questions? Or you can spend some time to look into the documents that we provide you, and let us know that next week. Okay? So that's it for the day. Do we check the attendance? Okay. As well. So please do the attendance check.